Yeah, good?
It works.
Cool, thanks man, cool. All right.
Hi everyone. We are going to start with introduction to an OpenStack chapter of Shmuel, pronunciation of the developer. Please enjoy.
He did work on my name for a couple of years before. All right, so hello everyone. My name is Shmuel Boudjnah. I'm a developer working for Innovance, which is one of the cloud companies you saw the logo on, which contribute to OpenStack and is one of the gold partner. And I'm going to be here to introduce you about OpenStack Swift, which is the object storage of OpenStack. So I've been working with Swift like before it was OpenStack exists, so a long time ago in Rackspace, and I've been involved with OpenStack since the beginning, doing all that kind of stuff, but mostly object storage and identity actually as well. So let's start. So first of all, I'd like to introduce about what's object storage. So I'm sure a lot of you, heard about it actually at least, or you at least know what S3 and what does S3 does. So if you want to do like the very, very high level overview, it's a big hard drive that sits over there somewhere, and where you can store stuff there. But it's not like a hard drive like the way you see it like normally on like that you attach to your computer. It doesn't have any POSIX interface. It doesn't have. It has like just an API. It has an API that you communicate with, and you're using it like to upload object, part, get, and do stuff with it as well in a very smart way. The advantage of it is that it's massively scalable, so you don't have like any single point of failure. You can share it like to everyone, and you can run that on community hardware. And so there is like these days, like with the cloud and all the marketing terms that people have been put like everywhere, there is that new acronym that start to that people start to say. It's the software-defined storage. So it's the same thing as what you define like with software-defined network, which is basically they say like you can run massively scalable system on community hardware and in a very efficient way. All right, you see how cool is it? And so what's the use case of Swift of an object storage system? So it's usually for public cloud, so as Amazon S3, Rackspace Cloud, HP Cloud, Internet and stuff. So they all run Swift except Amazon S3. And those are pretty big clouds, and you're allowed like, to have multi-tenants. So you have like multi-tenancy between things, and you pay as a service, like as much as they use, whatever they used, you get them like to pay for it, for the storage. Or you can use that for the private cloud as well. So you have like you have your own system, you have your own couple of developers, and you want like to have a place like to store stuff. So what kind of stuff? You can do like backups. It's a good use case, like object storage system is a good use case for backup. You write once and you read never. So you basically do like some long-term archiving, and you just want like to have like a very efficient way to do that. And you have disaster recovery. So you just spin up like a data center in Alaska or anything, and you want like to have all your stuff like as a disaster recovery somewhere, and it's a very efficient way to have that, and then to spin up like a Swift cluster there. And you have like a very good use case that most people will use it as a developer, is that for web content. So you get like a website that start to get like a lot of hits and a lot of traffic, and you want like to handle the traffic. You're not going to install like on Apache and serve that in Apache directly, or with all the other like web server. You probably want to have like a system that's been designed for that to serve files, and that's what Swift can give it to you. You have like other stuff like static websites. You know, like I don't know if you've seen like Jekyll's and tools like that. It allows you like to generate like blogs, like without having like dynamic content. You just want like to generate your your dynamic on your local machine, and after you just upload like the static HTML directly to the cloud, and you have like a free, super efficient system to serve all your files. And for large object, large backup. So large backup, scientific images, even the NASA, like, I don't know if NASA is actually using, but anyway, like it's a use case for the NASA, store fancy images from the moon. And it's as well, like if you come back on the OpenStack side, it's a storage system for your cloud. So when you have like a Nova system, the compute part, that's going to spin up VMs, and you're going to store those templates. You can store them in the cloud, or you can archive your cloud and your VMs directly in Swift. And Swift has a great integration with OpenStack. So that's the use case of why you use. That's the general overview and stuff. Don't worry, we'll go on to the technical stuff soon. So just before the technical stuff, that's like the fancy story, the fancy like a Wikipedia entry. So Swift, like where does the name come from? So usually when you say Swift in English language, it means like go quickly, go fast, blah blah blah, happening quickly. Well, it's as well a bird, and describe a bit what Swift design has been, and what's the philosophy. And it's very pompous a bit, but it's a nice like to have. All right. So it doesn't work anymore. Cool. So the API. So from my client's level, what the API is, it has a simple REST interface. It's like whatever you use, like everybody knows REST and how it works. So he has like the normal like get, post, delete, head options. We use option for calls. I don't know if you know calls. I'll explain it a bit later. And he has like simple response code, like that's very like people knows how it works. Like it's very simple. Like 2 is good, 3 reject, 4 is bad you, and 5 is bad Swift. And we have like a bunch of binding, like library binding that you can do with different language, like JCloud, Fog, PKGCloud, LibCloud, and we have as well like an external middleware that's not been Swift with Swift, which is like a S3 API. So doesn't offer like everything of S3 API because it's complicated to do that. But it has like all the basics. So basically, if you have like something that's been written with the S3 API, you can just you can just install that middleware, and you can have like your application with minimal change on it. So that's from the client's point of view. So the design of Swift. So when we started to design Swift, we had like a few global motto that we wanted to make sure that we achieve. So you know that when you start to design like those massively scalable systems, you know that at scales like everything is going to break. So don't trust anything. Don't trust anything in your architecture. Like you need to know that you're going to be able to scale like your every components and everything on your architecture, because like things breaks all the time. And we've seen that like on the public cloud, on large systems, and even on small systems, like you need to make sure that everything is really, it works very well. And that's what we did like when we designed Swift. Rare stuff can actually happen a lot. So stuff that you don't really realize when you, like as a developer, when you start to do some writing code, that you can put like some tiny little change, and you can like do like crazy stuff, like fill up disk pretty quickly. So I'm taking that as an example that we did I don't know, like 4 months ago, we started to depreciate like an interface of the middleware like inside, and we just put like a tiny depreciation warning, and people like came back to us like a couple of weeks later after the release, and they were like, dude, it's like all our stuff has been writing with all that depreciation warning because the middleware was not updated. So it's that kind of stuff that's like we try like to achieve and make sure that we don't do like we design for big architecture and massively scalable architecture. And simple is better than complex. So Swift system like is, when you look at it, it's very simple. So even like as a coder, like when you start like to dig into the code, it's trying to keep as simple as possible. Doesn't mean like it doesn't do much because it's simple. It means like it's pretty straightforward. So it's pretty straightforward to figure out the code and how it works. A lot of stuff has been done like in the mind for DevOps. So So we want, like as a developer, we want as well to have the ops, like when they're going to interact with a Swift system, they're going to feel at home. So that means like when you, for example, like the object, I'm going to go like more on that. When you store objects on a disk, we don't do any fancy binary data that goes encapsulate with like blah blah blah. It's just the object itself, so people can investigate directly the object. And when you, in all the components talking together, we don't have like a queue or like some weird protocols or binary protocol that goes together. We have REST interface, so even internally, like everything is talked to REST. So when the proxy server connects to our account, blah blah blah, all those stuff do in REST. So that goes like for the ops and make life easier for the ops. So a little bit of history, how we came to Swift. So at first, it all come from Rackspace originally. So at first there was Rackspace Cloud V1, and it was the like say simple way of doing object storage. It was like very straightforward, like the way you'll solve like in a very like I need to put something out there. So you have a bunch of object storage. And you have bunch of servers, and you have bunch of objects, and you want to know like where is the objects goes to which object server. So what we do, like you're just going to put some database, and you're going to be aware of the disk space, and you're going to round robin between the things, or like just adjust with a thing. But obviously the PostgreSDB was filling up pretty quickly, and it get really like crazy. So the people who were designing it, they were not, they knew what to do. So the plan was to use like something like Cassandra or stuff like that going to replace the DB, so to do like in a very efficient way. But Cassandra in 2009, I think, wasn't like really ready at the time, and so a team in Swift like started to get pulled together to start to work on the V2 version. And so we see it, and we started to completely redesign the thing. And we started to base ourselves on the placement based on logical placement. So we don't do that. So we don't have any DB or anything. Everything is distributed, and there is no single point of failure. And everything works by logical placement, which I'm going to explain next. And we worked closely with ops. So we had like a bunch of ops, and we had ops like working with us and trying to get us like infos and stuff and things, or we can make it better. All right. So let's get into the technical gory details. So the design of Swift. So there is like 4 components of Swift that are like the basic components of Swift that you know about. So you get like the proxy servers. Proxy servers are literally like the first entry to a Swift. You get the storage servers, that's the one that's going to store stuff on it, the objects. And you get the ring, which is the logical placement I'm going to explain. And you get as well the replication. The replication takes care of replicating everything. So in Swift, all objects that's stored in Swift have a URL. So there is no magic stuff or magic thing happening. Everything has an URL no matter what. Everything has by default like 3 replications that's going to stay like unique as possible. And all objects like have their own metadata. And developer interact with the system with REST API, like I said before. So that's mostly the overview. When you so the proxy server. So the proxy server is really the entry point. So it's the public facing, the public face. It's actually the one who's going to do a lot of work. So because like everything will go by here, and it's going to be the one that's going to store the data. So the way it works is that you get a client coming through. It's coming and say like I'm going to do a put on that server. So we already authenticated. We already like validated the token. We had a token. We validated it, and we good. So what the proxy is going to do is that it's going to take that object, object, and is going to determine it like where to store that object on the different servers. So we do that using a ring. And the ring is like it's using a consistent hashing technology to do that. So we take the object, sorry, and we put it like in the object. So we determine it with the object. We put it on the servers, and when we have a quorum that of at least 2, then we come back to the client and say we've been uploading the object with a 200, and everything was 201, and everything was working well. So at least we have a quorum of 2, and the rest will be eventually consistent. So what it means, like with eventually consistent, I didn't put that on your slide, but I should have put it, is that Swift is eventually consistent. I don't know if you know eventual consistency, like when you design systems, is that some part of a system can be is not going to be strongly consistent, which means like it's not going to be updated like when you do the action itself. So in case of Swift, is that when you upload a object, it's not going to update the container listing, the container which I'm going to explain after. It's going to happen after, so it's going to eventually get consistent. Usually, it would get like pretty quickly, like to be updated. It would be like literally as long as you do a put, like straight away when you do the get, you'll get the update. But it depends of what's the workload going on your service. So basically, the philosophy behind that is that you want to be able like to upload object really quickly and let people using Replicate be able like to do the get as well really quickly. So the get and the put will be really fast. After the listing would be eventually consistent. So and the proxy, what it does is like it's doing the response coordinations. So it would coordinate the response and would make sure that all the components have been saying like a 200, and that's been uploaded the object, and the object is there before it's going to acknowledge to the client that it's been uploaded. If there is like a server that's been failed, it's going to detect it, it's going to be the one detecting it, and it's going to go like to the next server using a logical placement. So the logical placement, the ring. So the ring is a complicated thing to explain. I'll be honest with you. I've been struggling to explain like in a kind of very simple terms, especially for people who's not been exposed to it. So the way to see it, so you get like constant hashing. Constant hashing, I'll have a different slide after that I'm going to show you to explain that. Maybe I can go like right now. So constant hashing is basically what it says. You take a URL and you put like the account, container, and objects, and you're going to take it and you're going to hash it. So you're going to do a unique number. And you're going to try to match whatever you have like on the server with like within the server, like the hard drive and the partition, and which partition is going to be what's the closest would feel like the object would get there. And it's not a real constant hashing because it has a bit of a twist in Swift, because we have like what we call availability zones. So we have different zones that you can put. Those availability zones usually like as a ops, you'll define them in your data center. So you are going to say that it's different cooling system, different networking, and you're going to say like those 3 availability zones are going to stay like somewhere else. And Swift is going to ensure when it's going to do the placement, when it's going to put the object, to put them like in different ability zones. So the way it works is that the availability zones, like when you start like making your ring, you have a bunch of commands that you use, and you're going to add devices, and at generation time is going to do like all the placement, like it's going to generate all the placement of the UID namespace, and is going to generate later against whatever device you put. So if you want to picture it, is that it's a great example that the ops at Rackspace Cloud gave me, is that you need to see it as a yellow page. So the yellow page, you take a yellow page, you just go over, and you know that this name I want to know like for which phone number, and you just get there, and it's literally what the ring is like it's a yellow page that gives you a map from one object to which server. So he has a new concept as well that's just getting introduced for Grizzly, which is a region support. So we've been working on, like the Swift dev have been working on a global cluster replication. And one part of it is to change the ring to be aware that there is going to be like different regions that can be sitting somewhere like in different data center. And you need to be ensure that at least one replica could as well go there to that region if there is so the placement will be going there. So basically, like the way you need to see the ring, it's a yellow page that like it's a pointer from the object to which server it is. So one advantage of using the ring is like when you're adding like new nodes, it's not like a modular thing, like the logic of placement. So when you add like new stuff, it's not going to affect like the different entities. So there's not going to be that much replication going on. But having said that, is that there is still like when you're adding like a new storage node, like a new hard drive, you don't want like to put it like just like that straight away. You want like to do gradually because a lot of shuffling still are going to happen on your cluster, especially on a large cluster, and obviously networking is going to be fill up networking and going to be bad for the service of your cloud. So on the ring you have as well a weighting system. So you can say like I'm going to put like a 2 TB hard drive into the ring, but I'm going to put like only 30% of it. So I'm going to do a weight of 30. And so it's going to fill up 30, which is going to be minimal on the cluster. And gradually you can do that like to 100. There is a tool as well that can help you doing that and doing like in staged like environment like to increase your capacity of cluster. There is one thing that need to be aware when you develop that is like the ring is not, there's no components that synchronize the ring. It's up to you to synchronize it. So that means like every component of the system in Swift have the ring sitting there with it to know like where is the placement of the other objects. But that ring is like synchronized by you. So usually the way it does, even like in a large public cloud, is that you generate your cloud and you put that like in a management server, and after you just push it like to all the nodes. And you don't need to make sure that you have the latest one because Swift logic, like by the logic of the proxy server, can ensure that it will go like to the latest one, and the object will be fine. So just the ring, as I was explaining. So it would try to get like the object, and we'll try to get the object like to the right place. So the right place. So the way it works is that you get like different server at different place of the ring, and the proxy server will try the first one, and second one, and the third one, like in a logical way. And if it fails, it would go to the other one, and it would use like the mapping of the ring to do that kind of thing. So the account container server is way more is more simple. Those two are mostly the same, even from the code point of view. Is that it's just a listing. So account would list like all the containers, and all the container will list all the objects on the server. So it uses SQLite database. So I know I had like bunch of queries sometimes, like in conferences when I speak about Swift. It's like, can I replace SQLite with whatever DB? And I'm saying like SQLite is just right there, like just to give like info, like it's local, it's easy to replicate, like with rsync and stuff. And we just use it. We could have used like a text file, but yeah, we're not going to reinvent like a SQL parser or a parser to the query. So it's a very efficient way. So he has like a very simple schema inside. He has like a table for listing, a table for metadata, and he has all the stats that gets eventually updated about like the size of the container or the accounts that gets there. There is one scaling concern, is that SQLite or text file for what it was. Can get you a lot of IO weight. So there's a lot of operation. When there's a lot of concurrent operation, like at very large scales, you can have a lot of Huawei going on. So the way to solve that, you have rate limiting. There's the option of rate limiting in Swift. So our clients cannot like just hammer like the same thing doing metadata updates and to hammer the SQLite. Or you can just put more money at the problem and just put the SSD. And SSD will be very efficient for the container server and the account server. So the object servers, as I said before, is like you use the file system itself. So when you store, you'll see the file like on the same file as what you have uploaded. We just literally dumping the file as is. It use like the X attribute, which is the extended attribute, some feature that you have on file system that exists on XFS and ext4, probably Btrfs and everything. It's where we store the metadata. So we don't store that in a database anywhere else. We store with the objects like those X attributes. The files are named by timestamp. And if there is like concurrent upload, the last one will always win. The deletion work with Tombstone, with a Tombstone system, which like you have, it does a deletions. You put .ts, and after like the replication system, when it sees that, it will be the one deleting the file itself when it's going to bounce. The directory structure is very simple. You get mount the data directory, the partition, the suffix, and the hash and the object. So why we use suffix? Because I don't know if you've seen on file system when you have a lot of objects in a directory, which can happen which is designed for that. You can have like a lot of what's the dir, inode dir, like a bunch of inodes and a really long way. So we just suffix it everything. So the replications, the replication is asynchronous. It uses a peer-to-peer replication process. It traverses the local file system and to detect the change, and it just go over and would use like to perform operations. But he would try to balance it like across different physical disks. He has like a system of a push model. So it's the server itself that would push his file to the others, and same goes. So everyone will be pushing to the others. It's the duty because they need to be ensured that to like whatever they get, like where it belongs. And they're all aware like of where things need to belong normally, because that's what the ring gives. The DB replications, the DB replication is like it's a bunch of hash that gets low-cost hash with that gets replicated in between 2 DBs, and you get like and you get compared like you go like by bunch of rows that gets replicated between the thing. If you don't have any DB, any SQLite DB, then you would do like just an rsync directly. I know like I'm missing time. So the object replication is using rsync on the backend. So we literally use the rsync command because we didn't want to re-implement like rsync directly, obviously. So we just use like the rsync, and it's only sync like only a subset of directory. So you use like a hash to invalidate. So basically it's a file on that directory that whenever there is an operation going on that one, it would invalidate it, and it would know like this place will need to be synchronized. So it doesn't have to travel to go like all over the directories like to be able to synchronize it. And it's usually like the scaling up of that is usually bound like the first time is going to be taken long, but when you have like the kernel caching all the inodes, then it will get much more efficient after. So that's a bit like how the application, how the system works. From a technology point of view, so what we use like on the system itself and how it works. So first it's Python. Good thing we don't have to do that in Java. And it's not really complicated, as I said before. It's very straightforward to look at. Like everything is pretty simple to figure out. Like they kept that mentality all the time. We use by default eventlet. So I don't know if you know eventlet. I know there's great sessions going on after. So it basically allows you to do non-blocking system, non-blocking operations with a kind of blocking kind of statement. So the normal code that you write, you can do it like in an asynchronous way. We moved away from WebOb to what we call SWAB. So I don't know if you know WebOb. It's a library like to do like nice like to be able to interact like with web server and WSGI. We didn't use it because we don't use it anymore because it was such a pain to for the upgrades and the difference, like every time they upgrade like versions, we had to upgrade like bunch of codes because they didn't have like great backward compatibility support. So we have our own version of WebOb, and we actually have as well our pure Python Memcache client as well. We did one. The reason is like I'm not going to explain Eventlet the way it works, but Eventlet does like monkey patching on most of the code, like on the socket calls, so it can do like asynchronous like operations, and it does that by monkey patching most of the stuff. But Python Memcache by default is a C library, and that C library, like you can't do monkey patching on C library, so we had like to write our own in a pure Python. And as I said before, like we were not like crazy enough like to implement the full R thing, so we just use R thing directly. And that's mostly after like there's different daemons for different tasks, for like ripping accounts, for example, like deleting full accounts. That would be another task from other daemons. So middleware is what we use like to provide features on Swift. We have WSGI middleware, which is like the standard interface in Python. And I don't know if you know how it works, middleware. So basically you have a pipeline, the request comes through and it goes like go by different middlewares, and the middlewares like get like the request get changed by the middleware. So you get, for example, the host system, when it gets like an query coming through, is going to check if there is a header called host token, xhost token, which is supposed to be a token there, and after it's going to use that token, it's going to validate it to the host server to know if that token is a true token that still works. So it does that. It connects like to a host server, which normally should be a Keystone with the OpenStack Keystone server. And after, like, you would say like okay, or you would just deny it, and the request will continue and goes on and goes on. That's so there is like a lot of middlewares in Swift, and we usually put that in the proxy because those features are exposed by proxy. But you can have like as well on the account container, we can have like different middleware as well there. One of the middleware that's been used everywhere is called Swift Recon, which is like a kind of admin interface, usually for the admin, to get you like informations about all your Swift clusters and the time, the replication time, the CPU time, even and blah blah blah, and it's all exposed directly on the like Swift specific stuff as a JSON directly on each service. So that's a big dumping of feature that we have. So by default, we have a lot of different features that's been shipped with Swift. Where do I start? All the stuff that you expect, like quotas, account quotas, or container quotas. Large objects is some feature that's a bit different the way it works on Swift. So Swift doesn't allow you, for different reasons of the way it works, the ring, that to upload like a huge object, you're going to have to split it. So, but you have a support of so you split your files and you upload like a manifest file, which is like a 0-byte file that's going to list all your different objects that you split. And when you're going to when you're going to do a get on that manifest file, is going to concatenate all the objects together that you specify on that manifest to be able to serve the client and to get you can go as like 100 gigabyte of cluster. You have cores. Cores, I think it's a nifty feature. It allows you to, it's a standard stuff from the W3C. So the browser, when you want to upload directly to a Swift without going by a proxy, you're going to use some JavaScript, and the browser is going to connect to the Swift server when you're going to do a put directly on there, and it's going to ask, can I upload there? And if your Swift is configured with the core support to say like this website is allowed to upload, then you will say okay, and you can directly upload like the client's file directly on your Swift cluster without going by your Apache or your app server. We have a bulk operation as well. That's something that people have been asking a lot. You will be able like to do like multiple delete at the same time, and you can have as well like upload like a tarball directly, and then you would like split it and upload to a directory. Sorry. What else? Like temporary URLs. You know those file sharing website that gives you like temporary URLs like for download only for now. So it gives you that kind of thing. You can as well versioning. You can open a container and say like everything that's happening on every object can have like a certain amount of versions, and those versions are going to be kept there. And that's it. So if you want to try Swift, it's very easy. And if you want to try OpenStack in general, you can come to the workshop after, or you can as well do that by yourself by downloading DevStack on devstack.org, which is a thing that we have on OpenStack, and you can configure like to use Swift. That's the end. By the way, my company is hiring. Blah, blah, blah. If you want cool people, cool company, cool technology, blah, blah.
So, everyone has questions?
Yeah, I probably know the answer already, but is it also possible to store many small objects, or is it rather good for few big objects?
I'd say yeah, it's good for small objects. You can have like the only part that's not good for it's when you have like the thing that I put like on my slides, when you have a container like stuff like operation on metadata on the containers. So of the SQLite, so there is the SQLite will be like queuing the request, and you'll have like IO wait. You can store. You have no problem like to store like large objects or small objects. It's good. It's mostly good for both of them. It's only like on the container part when you have like different things. So it has like a lot of concurrent metadata update. That's where like it's going to be bad. So to answer your questions, like you can as well store like a small object, and you get like a good thing for that. You'll have you need to increase your networking for large objects. So if you have like a bunch of gigabytes of like objects, and you only serve those, the proxy server is going to keep that connection, is going to recreate it as well with the large object support. So your proxy server needs to be increased. So it needs to be spread out. So you need to have like multiple of them, because your network connection will be hammering it. So just to come back on that, like on the thing, like from an operation point of view, the way you want to install Swift is that just make sure to increase your proxy servers. So you do that like in a sorry, that thing is just in my head. So the way you do that is like you just put like a bunch of proxy servers sitting together. They all like can be independent. They don't have to share anything except maybe the mem cache, but that can be scalable as much as you want. And after you have a load balancer that's sitting in front of it, usually a check proxy, and those load balancer, that's a big point, does the SSL. So Swift doesn't do an SSL because it's very inefficient to do that inside Python. So you leave that to some load balancer that does all the SSL part. And after your load balancer, you increase you're scaling up the way like networking, blah blah, all that stuff, and people knows.
Great talk. Thank you very much for that. I was wondering, from a production environment, how do you ensure that your partitions don't run out of space, and how do you reshape that cluster? Because
good question. It's a good question. The way you ensure that is the way you do like you use your monitoring system. So the ring needs to be even. So if you start to fill up your disk, you're in big trouble. You're in really big trouble. So usually what you have is some threshold on your monitoring system that's going to monitor, and whenever like you have like this that goes like by 70%, or I mean I'd say 70%, like some other people who have different ideas about the cost to value and thing. But from 70 to 80, you'd say, whenever you get to 80, you want to increase it. So the way you do that, like literally, you just plug like a new servers into it. You plug like a new hard drive in there, and you add it like to the ring. But you add it like in a gradual way, like I was saying before. So you're going to put that like as only 30% of the hard drive is going to have a weight of 30. And after, like, the ring will take it and encourage you like to go on Google and try to see like how consistent hashing is working and etc. But some part of it are going to be shuffling, only minimal part. I think I'd say like 5% or 10% of each one. So those stuff are going to fill up. But only, you say like before, only 30%. So only 30% of it is going to be shuffling there. And after you just increase, and you add in more capacity to it like that. So there is I did an overview, to be honest. Like there's much more than that, and I would encourage you like to go on swift.openstack.org for way more information on that. What I say? So just this one.
Hi.
So
This next guy.
Hi. I was wondering about the versioning support, and do you support like HTTP patch requests for updating a small part of a large object?
It doesn't. I know that there's a guy who sent that kind of thing like 2 weeks ago. It was like really recent. So we don't have support of patch and the verb patch as well, the HTTP REST patch, because of the eventual consistency of the thing. I don't know the details, but I know the review didn't patch for different because it wasn't like efficient. So I think so we don't support it. So usually, literally, what it does, like the versioning system, is that whenever you upload like a new object, it would keep it like a version and will update the other one. I think there is one question.
Actually, the time will be over, but if you want, we can still some time for a coffee break. Otherwise, you continue the coffee break. What we will do?
Yeah, you can. I'm here all the week. I'm here on the internet as well.
So, thank you. I want also to